Hello, everyone. In this presentation, we're going to talk about the prediction of the stress field in composite materials using neural networks. This study was conducted by Noah James and myself, Marwa Yacouti. First, let's start with the motivation of this work. So composite materials are multifunctional materials, which means that they are used in a variety of applications, such as civil, aerospace, and mechanical engineering. One of the challenges that faces composite materials is the prediction of stress field under a given loading conditions. Finite element analysis is the widely used method for stress analysis. However, when applied to composite materials, this method becomes computationally expensive. That is why there is a need to develop an accurate, time-saving, and more efficient method to replace finite element analysis for composite materials. And neural network is, in particular, it stands out as a promising approach for stress field prediction, and that is the focus of this study. So here is the limitations of the existing methods that used neural network. First, the proposed techniques focused mainly on the overall stress level and not on the local distribution of the stress. And second limitation is the small size of the available data set. In the study, we proposed two methods. The first one is to use data augmentation techniques, and the second approach consists in using unit architecture, since it's more effective on small data sets. This slide shows the fiber reinforced composite that we consider. So we have 4 fibers randomly distributed in a matrix. We use finite element analysis to generate the stress distribution, and then we transform it into regularly separated grids using interpolation among neighboring data points. So our data set consists of the geometry as input and the stress field as output, and we used the dataset provided in a study conducted by Feng et al. So here is the architecture of the encoder-decoder structure that we used. It consists of 3 convolutional blocks followed by 5 ResNet blocks and 4 deconvolutional. The components of each one of these blocks is described in this slide. We split then the dataset into 80% for the training data, 10% for the validation data, and 10% for the test data. Next slide shows the predicted stress field that we obtained using 1,000 samples. The accuracy of the model was determined based on the mean squared error. So here you can see the relationship. And so using 1,000 samples, the test accuracy was equal to 66%. In next slide, we will see the effect of the data augmentation technique. So for data augmentation, we used 3 methods. The first one was to flip the geometry and the stress field horizontally. Then we did flip it vertically, and then we did a 180-degree rotation. And next slide, we can see the training and test loss that we obtained for each one of these data augmentation techniques. So we can see that for 1,000 sample, the test accuracy was equal to 66%, and for 4,000 samples, the test accuracy was equal to 85%. So we can say that the test accuracy increases as we increase the size of the data set. Then I'll leave you with the second approach that will be presented by Noah.
Thank you. So now to kind of talk about the architecture experiment we did, which involves just replacing that ResNet architecture. There's obviously room to improve in pretty much any domain, but especially in this one on the architecture. And so we identified a few different kind of next steps for what a successful architecture would look like. Among those included achieving high performance even with low volumes of training data, and also to reduce noise in your outputs. And in considering these goals, we proposed to test the UNet architecture on this same composite data set. The UNet design is fairly standard. It's modeled after the autoencoder architecture, with the only difference being the concatenation of features from the encoder side to the decoder side. So on the encoder, you'll do convolutions to reduce the dimensionality while increasing the number of channels. And on the decoder side, you will use transpose convolutions to increase the dimension size. So They're perfect mirrors for each other. And so that allows you to concatenate features across and retain global information from the first couple of layers, and also reduce the inherent noisiness of the autoencoder bottleneck, which happens when you decrease your feature space down to that latent space at the bottleneck. So looking at the results for this experiment with using the UNet. Unfortunately, the UNet performed not as well as the ResNet baseline in basically any error metric. As we can see, all the error rates are much larger on the UNet side, and I'll kind of go over why that is the case, because it's not as simple as it just being worse. And looking at the stress contours, for just kind of a qualitative analysis, we see that the ground truth is fairly comparable to the ResNet and the UNet. The UNet has a much smoother contour, but geometrically it's a little bit smaller than the ground truth in this particular example, whereas the ResNet more closely mimics that circular part in the middle. And looking at more examples, you kind of see UNet looking exactly the same in every single sample, which means that it's overfitting and trying to output the same thing every time. Conversely, the ResNet is more closely following the ground truth and changing the geometry. The only issue being with the ResNet is that it has all this noisiness. You can see that granularity in the data. So in this work, we've demonstrated the effectiveness of image data augmentations for composite geometries and stress contours, because as the dataset size increased, we saw that those random flips and rotations would improve the accuracy on the test set. On the other hand, though, the neural network architecture experiments were inconclusive at best because of the overfitting problem. But fortunately, the smooth stress contour outputs of the UNet show that it can be used in future works where those hyperparameters are optimized and maybe regularization can be introduced, so that way it can bypass those autoencoder models that are more noisy. So that is all. Thank you for listening.